of the project titled Lung RetinaNet Lung Cancer Detection using a RetinaNet with Multi-Scale Feature Fusion and Context Module. Introduction. Lung cancer is a serious disease characterized by abnormal cell growth in the lungs. It has a high mortality rate, especially because it's often diagnosed at advanced stages. Early detection significantly improves the chances of successful treatment and patient survival rates. Therefore, timely identification through screening and diagnostic methods is crucial. Existing methods like sputum cytology, CT scans, and X-rays are commonly used for lung cancer detection. However, they have limitations. Sputum cytology, for instance, does not detect small tumors accurately. CT scans and X-rays can sometimes miss small lesions or lead to false positives, and they are not easily accessible due to cost or resource constraint. Traditional machine learning approaches like support vector machine and random forest require manual feature extraction. These techniques struggle with complex data patterns and can have challenges generalizing to new unseen data. They heavily rely on predefined features which does not capture the intricate details necessary for accurate lung cancer detection. Deep learning, a subset of machine learning, has shown promise in various medical tasks, including disease detection. Deep learning techniques, especially convolutional neural network, can automatically learn relevant features from raw data, potentially improving accuracy in complex tasks like identifying lung tumors. While deep learning models have shown potential, many existing models primarily focus on simple classification tasks and might not be adept at accurately identifying early-stage tumors. Early-stage tumors can be tiny and harder to detect, leading to potential misdiagnosis or oversight. The Lung RetinaNet is a novel deep learning-based model specifically designed to address the limitations of existing models. It introduces several innovations such as Feature Fusion Module. This combines information from different sources or layers to enhance the understanding of tumor features. Dilated Context Module. It helps the model capture a broader context around tumors, aiding in the detection of tiny lesions. Adaptive Anchors. These adapt to various sizes of tumor, enabling the model to better detect both large and small tumors. Objective. The primary goal of the project is to create an automated system, the Lung RetinaNet, utilizing deep learning techniques. This system aims to address two critical aspects of lung cancer: efficient tumor detection and severity assessment. By leveraging deep learning, the objective is to develop a robust and accurate tool that can automatically detect lung tumors and assess their severity without human intervention. Existing methods for lung cancer detection often struggle with accuracy, particularly when it comes to identifying early-stage tumors. These methods misinterpret small or subtle signs of tumors, leading to lower accuracy rates, especially in detecting tumors in their initial stages. The Lung RetinaNet model is proposed to specifically target the challenge of accurately detecting tiny lung tumors. It plans to achieve this by incorporating two key modules: multi-scale feature fusion based module and dilated and lightweight context module. Apart from detecting tumors, the Lung RetinaNet also focuses on accurately localizing them within the lung images. It plans to achieve this by integrating contextual information at different stages or layers of the neural network. This means that as the network processes the data, it will continually incorporate information from the surroundings of the suspected tumor regions, potentially improving the precision of tumor localization within the images. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages in the chosen programming environment. This usually includes libraries for deep learning frameworks such as TensorFlow or PyTorch, data manipulation like Pandas or NumPy, and image processing such as OpenCV. Exploring the dataset. Lung cancer classification. This likely involves acquiring the dataset specifically tailored for lung cancer detection. It contains various classes or categories related to different types or stages of lung cancer. Lung cancer detection from RoboFlow. RoboFlow is a platform providing pre-processed or annotated datasets for machine learning tasks. This dataset have images labeled with information about lung tumors, aiding in model training and evaluation. Image processing. Image data generator. This is a functionality often found in libraries like Keras for TensorFlow that assist in real-time data augmentation during model training. Augmentation techniques such as rescaling, sharing, zooming, flipping, and reshaping images are applied to increase the diversity of the dataset and help the model generalize better to unseen data. Rescaling the image, shear transformation, zooming the image, horizontal flip, reshaping the image. Torch vision based processing for detection. Torch vision, a part of PyTorch, likely contributes to specific image processing tasks tailored for object detection models. This involves transformations, data loaders, or custom processing steps required for the RetinaNet architecture. Building the model. The primary focus is on constructing and training the deep learning architecture to perform lung cancer detection using the RetinaNet framework, with emphasis on multi-scale feature fusion and context modules. Training the model. This step involves feeding the prepared dataset into the constructed lung RetinaNet model for training. The model learns to detect lung tumors by adjusting its parameters to minimize the defined loss functions. Training typically involves multiple iterations, epochs, where the model learns to improve its accuracy in detecting lung tumors. Flask framework with SQLite for sign-up and sign-in. Using Flask, a web framework in Python, to create a web application. Integrating SQLite, a lightweight database for user authentication with sign-up and sign-in functionalities. Users can register accounts, sign up, and login sign-in to access the lung tumor detection service. User upload an image for analysis. This module allows registered users to upload lung images they want to analyze for tumor detection. The uploaded images are sent to the backend for processing and analysis. The given input is pre-processed. The uploaded images undergo pre-processing steps similar to those used during training. Pre-processing involves resizing, normalization, or other transformations to make the input suitable for the model's inference. The trained model is used for predicting the result. The pre-processed image is fed into the trained lung RetinaNet model. The model predicts the presence and location of lung tumors based on the input image. Final outcome is displayed. The predictions made by the model are processed and displayed to the user. The outcome includes information about detected tumors, their location, and potentially their severity or classification. Users can visualize the results through a user-friendly interface, allowing them to interpret and understand the model's findings. Algorithms used. To implement this project, we have utilized the following algorithms. In the classification, we have used the following algorithms. The first one is VGG16. Visual Geometry Group 16. VGG16 is a deep convolutional neural network known for its simplicity and effectiveness. It's widely used for image classification tasks. The architecture comprises several convolutional and fully connected layers. DenseNet 201. DenseNet is a densely connected convolutional network where each layer is connected to every other layer in a feed-forward fashion. DenseNet 201 specifically uses a larger architecture, providing higher accuracy for image classification tasks due to its depth and connectivity. EfficientNet V2. EfficientNet is a family of convolutional neural networks that achieve state-of-the-art performance by scaling network depth, width, and resolution in a balanced manner. EfficientNet V2 is one of the variants tuned for balancing model size and performance, making it efficient in terms of both computational resources and accuracy. ResNet 101. ResNet, residual network, introduced residual connections to tackle the vanishing gradient problem in very deep neural networks. ResNet 101 specifically refers to a ResNet architecture with 101 layers capable of learning complex features and patterns. MobileNet V2. MobileNet V2 is designed for mobile and edge devices, focusing on efficiency while maintaining high accuracy. It utilizes depth-wise separable convolutions to reduce computational complexity while retaining good performance for image classification tasks. RetinaNet, object detection used in classification. While RetinaNet is primarily known for object detection, it can also be adapted for classification by considering its classification subnetwork. It's a two-stage detector known for its ability to handle object detection at different scales within images. In the detection, we have used the following algorithms. Faster RCNN, region-based convolutional neural network. Faster RCNN is a widely used object detection model consisting of two stages, Region Proposal Network RPN for generating region proposals and a detection network for object classification and localization. RetinaNet, object detection. As mentioned earlier, RetinaNet is a two-stage object detection architecture that integrates a feature pyramid network FPN with classification and regression subnetworks. It's known for its efficiency in handling objects at various scales. As an extension, we applied YOLO models to produce a more robust and accurate final prediction. YOLO, you only look once. YOLO is an object detection model known for its real-time performance and accuracy. YOLO models divide images into grids and predict bounding boxes and class probabilities directly, offering a different approach compared to region-based methods like faster RCNN or RetinaNet. The extension of applying YOLO models to the lung RetinaNet project likely aims to enhance the accuracy and robustness of tumor detection by leveraging YOLO's unique approach to object detection. Comparison graph. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the classification comparison graph. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. These are the detection comparison graph. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that measures the accuracy of the positive predictions made by the model. Specifically, it calculates the ratio of correctly predicted positive observations to the total predicted positives, irrespective of actual positives in the dataset. In the context of lung cancer detection, precision measures how many of the identified cases of potential lung cancer were actually positive cases. This is the recall comparison graph. On the x-axis we have recall score and on the y-axis we have algorithm name. Recall measures the ability of a model to correctly identify all positive instances from the dataset. It calculates the ratio of correctly predicted positive observations to the total actual positives. In the context of lung cancer detection, recall measures how many of the actual positive cases of lung cancer were correctly identified by the model. This is the MAP comparison graph. On the x-axis we have MAP and on the y-axis we have algorithm name. MAP, mean average precision, is a commonly used metric in object detection tasks like identifying cancerous regions in medical images. It calculates the average precision for each class, in this case cancerous regions in lung images, and then averages those precision across all classes. It considers both precision and recall at various thresholds to provide a single scalar value that represents the overall performance of the model. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address. This, which is the local host, and port, which is this. Now copy this local link provided by the Flash framework. I am copying the link and place this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on login. So here we need to enter the username and the password which we have created and then click on submit. We have logged in successfully. So first we will do the classification. So click on classification. So here we need to choose the file. So click on choose file. So I'm selecting the case 1. Click on open. Now click on upload button to classify the image. So here this is the uploaded image and this image is predicted as benign. Benign is a non-cancerous or non-threatening lung abnormalities detected by lung RetinaNet, indicating harmless or non-malignant conditions in lung tissue. Now we will upload some more images. So click on try again. Click on choose file. So here I am selecting case file. Click on open. Now click on upload button. So here we can see this is the uploaded image and this image is predicted as normal. Lung RetinaNet categorizes lung images as normal, signifying the absence of detectable abnormalities or pathological condition in the lung tissue being analyzed. Let us upload one more image. Click on choose file. So here I am selecting the case 4. Click on open. Now click on upload button. So here we can see this is the uploaded image and this image is predicted as malignant. Lung RetinaNet identifies potentially cancerous or harmful anomalies within lung images, indicating the presence of malignant or cancerous growth. So in this way, by uploading the images, we can classify them as benign, malignant or normal. Now we will do the detection. So click on detection. So here we need to upload a file. So click on choose file. So here I am selecting the case 1. Click on open. Now click on upload. So this is the uploaded image and this image we can see that benign is being detected in these regions. Now we will upload some more images and check the detection. Now click on choose file. Click on upload. So here we can see this is the image which we have uploaded and here we can see the detection that it is a normal image. Let us upload one more image. So here we can see this is the uploaded image and in this image we can see that malignant is being detected and malignant is present in these regions. So in this way, by uploading the image, we can detect the specific regions where the malignant or benign disease is detected. Now click on sign out. The conclusion of the project is the lung RetinaNet model designed for lung tumor detection exhibits notable advancements in accuracy and overall performance when compared to existing methods. This improvement could be attributed to the model's sophisticated architecture and innovative modules designed specifically to address the limitations of conventional methods. The model incorporates a multi-scale feature fusion based module that combines information from different scales or levels within the network. This fusion enables the model to gather a more comprehensive understanding of lung tumor features, improving its ability to detect tumors of varying sizes. Additionally, the inclusion of a dilated and lightweight context module assists in capturing a broader context around tumors without significantly increasing computational complexity. This context awareness aids in the detection of minute lung tumors that might otherwise be overlooked. By integrating contextual information at each layer of the neural network, the model becomes adept at precisely localizing tumors within the lung images. This contextual understanding allows the model not only to detect tumors but also to provide accurate information regarding their positions within the images. The lung RetinaNet model's performance is rigorously compared with other contemporary deep learning based approaches, possibly including architectures like VGG, ResNet, or other specialized models developed for lung cancer detection. In these comparisons, the lung RetinaNet model demonstrates superior detection accuracy and more promising results in identifying lung tumors, thereby establishing its superiority over existing state-of-the-art methods.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Project's YouTube channel and subscribe.